We'll use a 4-laptop cluster on which we will deploy these applications first and then migrate the MySQL database first to the AWS cluster and then back from AWS cluster to the laptop. We will use a new technology breakthrough in computer science that infuses cognition into Turing machines in the form of meta-containers. With the meta-containers, we can actually configure, monitor, and control any application or runtime service such as MySQL, Apache, Tomcat, etc. It's like having your own system administrator at runtime with all the monitoring and control which we exploit in this demo to create policy-based runtime application management without depending on infrastructure management systems, myriad other tools. Very cool. This picture shows how the meta-containers are used and services configured and deployed. We do not change applications or runtime services or the operating system. We do not change infrastructure or depend on Amazon Web Services or data center management systems except for provisioning the servers and virtual machines. We deploy the same OS, meta-containers, and services in physical or virtual server clusters provisioned to meet the application needs. Developers do not change their development process or environment. No need to deploy Ops API in your functional logic. Non-functional requirements are managed through a clever architecture that allows runtime policy-based management and adds or deletes servers to the distributed computing cluster. As you can see, we have used this architecture to deploy the service and provide the managers of these services and the manager of managers of these services so that we can create workflows and manage these workflows in a very elegant way. It allows us to do runtime service management for every application or service, and we can also dynamically compose to create a workflow and manage the workflow itself. The developers develop their applications and databases just as they do today. No PaaS is required. No awareness of infrastructure as a service is required. Once the distributed computing cluster is provisioned and the meta-container platform is deployed both in the laptops and on the Amazon Web Services, we detect all of the nodes in the form of an application network in our GUI. All we have to do now is to be able to select the platform and the node and upload the actual applications or the databases just as the developer has developed. Here is the configuration that shows the Apache, Tomcat, and MySQL deployed in your physical cluster. In PL002, for example, we have uploaded the MySQL and its database, which is called the transaction.tam.demo, and Tomcat with its application war file, which is Tomcat transaction.tam.demo. In addition, you see in PL003, Apache transaction.tam.demo application running there. Now we show here on the left hand side how you can select any one of these applications and scale them up, migrate them from one server to another server or one server to another virtual machine in the AWS cloud. We can also stop, pause, and remove these applications. This screenshot shows the Tomcat application designed to set the transactions per minute it writes into the MySQL database. We will choose 20 transactions per minute for the sake of this demo. This screenshot shows the Apache application essentially reading from the MySQL database the record that was written, which contains both the writer's IP address and the database IP address. This is intended to show where the MySQL and Tomcat applications are currently hosted. And when a migration occurs, this IP address will change accordingly. This screenshot shows the result of migrating with a single click from PL002 now to the AWS cloud in PL005. The MySQL database is now migrated to AWS cloud, and the Tomcat is still writing the same number of transactions, and the MySQL is recording them continuously. This screenshot shows the impact after migration. As you can see on the left hand side, the IP address of the MySQL database now is in AWS 25.99.70.121, and the transactions are continued to be written in the MySQL database as if nothing has happened. On the right hand side, I have shown the MySQL database records read from the MySQL, and as you can see, at transaction 210, the switchover occurred from 25.100.38.48 to 25.99.70.121. So the transition occurred between 210 and 211, and transactions were not interrupted. That means the MySQL database still is writing continuously, thinking that the database is still available, and the old MySQL is migrated to the AWS, and the new MySQL continued with its old records and also with the new records without any loss of transaction. In this picture, we now show that the database that was in the AWS cloud is migrated back into the physical server cloud, and now the database is moved to PL003, and the transactions again continue to be written on the MySQL database as if nothing has happened. This screenshot shows the transition occurring between 265 and 266, where the MySQL database was migrated from the AWS cluster to the local physical laptop. Now we will change the demo to show that we can auto scale the MySQL database, and it has some very interesting features. The auto scaled MySQL also is synchronized with the other MySQL so that you can have both databases identical copies of the data. So we are going to show now auto scale the MySQL in the physical cluster and migrate both Tomcat and Apache to the AWS cluster. This screenshot shows the result of migrating both Tomcat and Apache with a single click to Amazon Cloud and auto-scaling the MySQL in the physical cluster between PL001 and PL003. On the left-hand side, you can see the database records in PL001, and on the right-hand side, you can see the MySQL database records in PL003. Both of them are identical, which means that we have a synchronized database. This has very good implication that you can implement, for example, a multi-master MySQL database in a cloud without having to change the. What this demo shows is that we can now set new goals for the enterprise IT. We can drastically reduce time to market, time to fix, and eliminate complexity in current service delivery process in data centers, whether it is virtualized or not. We can also enable a single-click application provisioning, single-click distributed infrastructure provisioning, and policy-based application orchestration and quality of service during runtime. We can eliminate the current data center complexity involved in virtual machine image motion without changing current applications, operating systems, or the infrastructure and processes in the enterprise. We can also reduce the cost of managed virtual machines at least by 3 times, or not use VMs at all without losing the cloud features such as self-repair, auto-scaling, live migration, and on-demand provisioning. This also allows us to free the developers from having to deal with availability, performance, security, compliance, and cost issues at the development time and focus on business logic and deploy their applications, not worrying about DevOps API, PaaS environments, and the constraints of being aware of the IaaS, whether they are working in the AWS cloud or OpenStack cloud or a physical server-based data center. This will have a profound impact to the potential stakeholders. One is, of course, the line of business owners. They can now assure the quality of service by providing end-to-end visibility, security, and control. They can also get precise resource accounting because the meta containers provide accounting feature on how each application utilizes the resources such as CPU, memory, latency, bandwidth, storage IOPS, storage throughput, and storage capacity. On the IT side, the policy-driven visibility and control for developer workloads can be provided now without huge complexity. You can deploy the security and regulatory compliance, so all of that in the infrastructure provisioning process, and it is not impacting the service delivery and service provisioning. There is no cloud vendor lock-in. You do not depend on architecture of AWS. You do not have to compromise on mutability and statelessness of virtual machines. You can also eliminate VM tags if you wish. On the other hand, the developers have now the ability to use the latest, coolest development tools, no restrictions of PaaS, no need to learn new stuff. We also provide service composability with quality of service, service scalability, reliability, and security without worrying about architecture or infrastructure. This provides a way to converge DevOps for development, test, deployment. You can very easily deploy this same application network of services on a test pod or on a production pod, and it would exactly be the same. You will also have the end-to-end service visibility across the service component stack because you can create now history of these transactions in each component, and you can look at them and correlate them across the service transaction. I will conclude this presentation with some observation on potential key business outcomes. We can first decouple application reliability from infrastructure's reliability to ensure 100% uptime of mission-critical applications. By enabling differentiated service offerings based on pay for SLA, you can essentially provide platinum, gold, and silver types of infrastructure. Obviates the VM image management infrastructure, eliminates cost and complexity from all other distributed systems management tools and myriad management infrastructures. It reduces mostly the operational costs. True stateful mobility across physical, virtual, and cloud infrastructure allows enterprises to use best available resources at any given instant without switching overhead. Frictionless, zero switching costs. No application re-architecture to get mobility, scalability, HADR, and end-to-end security.